Good afternoon, all of you. Uh, my name is Nitin Tomar, and I am a PhD student in the Department of Mathematics. So, today we will be discussing, we'll continue our journey of what we have been learning since past few weeks in the numerical analysis. So, we'll first revise things that we have already done. So, in the last class, what we did is to define certain norms, some vector norms. So, okay, so recall that for a given vector x in Rn, we define three norms. First is L infinity norm, and what was that? L infinity norm was the maximum of the coordinates of x I varying from 1 to n, where this x is of this form x1 x2, because it is an element of Rn, so it will look like this. Second we saw was L1 norm, and it is basically the sum of the absolute value of each coordinate. And third is L2 norm, or the Euclidean norm, as we saw or the Euclidean norm, and it was defined to be this way. You take square of the absolute value of each coordinate of x, and then you take a square root, and this was your L2 norm. We have proved many inequalities, so here we prove one more which we did not prove in the last class. So let it be a question. Prove that norm of x1 is less than equal to root n times norm of x2. So the proof is not difficult. Okay. So note that, so we start with one observation. I not equal to j, we take this difference, and if you open it, it will be, you open it, so it will be mod xi square plus mod xj square minus 2 mod xi mod xj. Yeah. So this will be same as, summation mod xi square, I going from 1 to n minus 1 minus 2 summation mod xi times mod xj. And I not equal to j. Yeah. See why this n minus 1 has come into the picture, because yeah, because it will be I not equal to j mod xi square. Now there are n minus 1 j's which are not equal to I. So basically this is a double sum, okay, I going from 1 to n, j going from 1 to n, such that j is not equal to I at any stage, okay. So this sum is, because this is independent of I, so this will be precisely n minus 1, okay. Yeah. So this will be n minus 1 times of this. So hence what we have is the following: 2 mod xi times mod xj, I not equal to j, is less than equal to n minus 1 mod xi square, I going from 1 to n. Now if you add summation mod xi square both sides, adding this entity I going from 1 to n summation mod xi square, or we don't need to add, so this will directly imply, because this is what, this is n times summation mod xi square, I going from 1 to n, then minus summation mod xi square, I going from 1 to n. Now you take the minus summation mod I square on the left hand side, and what you will get is the following: summation mod xi square, I going from 1 to n, minus, plus summation mod xi mod xj, I not equal to j, is less than equal to n times summation mod xi square, I going from 1 to n. Now this sum is precisely equal to this sum is precisely equal to square of this, right, and less than equal to now if you look closely that this is precisely the one norm of x and its square, and it is less than n, and this is precisely the 2 norm of x and its square. So hence if you take the square root both sides, hence you will have norm of x1 is less than equal to root n times norm of x2, and this is precisely what we had to prove, so we have proved it. Yeah. Then we defined what we called as matrix norm subordinate to a vector norm. Subordinate to a vector norm. And what was that? By the definition, given Rn, so we fix a norm on Rn, and what we do, we take A in this an n cross n matrix, then we defined and one particular norm of A with respect to the norm defined on Rn, so it is norm Ax upon norm x, and of course x is not equal to 0. Now this norm is called the matrix norm subordinate to a vector norm, and as example we saw examples. Matrix norm subordinate to the number 1. So first we saw the subordinate to the maximum norm, that is the L infinity norm, or let me write it as it is, L infinity norm, and it is norm A infinity. And how will you define it? It will be because now we are choosing infinity norm on Rn, and this we in fact proved that this will be precisely maximum of the row sum. So you add one each row and you take the maximum of the sum. Okay, so this entity here, this entity, if you look closely, this is precisely ith row sum, ith row sum. Yeah. Second is L1 norm, and it is by definition it should be norm 1th norm of Ax quotiented by L1 norm of x and x not equal to 0, and we saw in the last discussion that it will be, so for maximum norm, for L infinity norm we need to take maximum over the row sum. Here we need to take the maximum over the column sum. Jth row sum, and last but not the least we saw the matrix norm subordinate to the Euclidean norm, which is the L2 norm. So by definition it should be this, and it is maximum square root of the maximum of the eigenvalues of A transpose A, where lambda 1, lambda 2 are eigenvalues of A transpose A, and this particular norm is called spectral norm of A. Why spectral norm? Because it uses spectrum of A transpose A. Spectral norm of A. Spectrum means, biospectrum we mean the collection of eigenvalue. Okay. So from here, so let us start with one example. In which we calculate each of these three norms so that you have clarity in your mind. Example, let A be 1, 1, -2, 1, 2, 1, or let us do more specific short example. It's a -2, 1, 0, 0. I am just taking simple thing. So first of all, norm A infinity, what it will be? It will be maximum of summation mod ij, now row sum, which means j going from 1 to 2, and I going from 1 to 2, right? See, we need to have the row sum. So this precisely means maximum of summation mod. When I is 1, so it will be 1j, j going from 1 to 2, and mod of a to j when j going from 1 to 2. Yeah. Now tell me what is this sum. Summation mod a 1j. So now mod a 1j, j going from 1 to 2, it is nothing but mod a 1 plus mod a 1 which is nothing but 2 plus 0, or let me write it more explicitly, minus 2 plus mod of 0 which is 2, right? And if you go to the second row sum, you will have sum of absolute value of a to 1 with the absolute value of a to 2, which is 0 plus mod 1 which is 1. So what is the maximum out of these two? The maximum is 2, right? So hence norm a infinity is 2. Okay. Now if you compute similarly one can check that the each, so first column sum is modulus is 2 and it is 1, so the maximum is 2 here. So again the L1 norm of A will be 2, not L1 norm, the matrix norm subordinate to L1 norm will be 2. Now the main thing is the spectral norm. So now we compute the spectral norm of A. So what will be A transpose A? So A transpose A will be minus 2 0 0 1 times minus 2 0 0 1. I took matrix very nice, okay, so that I don't have to do much computation, but in general matrix will not be that nice, so you have to be you have to do some computation. So what it will be, the product will be 4 0 0 1. Yes. Now what are the eigenvalues? So eigenvalues of A transpose A are nothing but 4 and 1, 4 and 1, and so the two norm will be square root of maximum of mod lambda, so okay, let us write lambda 1 to be 4 and lambda 2 will be 1. So we need maximum of lambda 1 comma mod lambda 2, which is precisely root 4, right? And it is 2. So this is how, see again, because the matrix is a diagonal, it is in fact a normal matrix, diagonal matrix. So It is very easy to compute norms in this case, but the aim was not to show the computation. The aim was to show how should one proceed for the computations. Okay. Yeah. So with this we end this example. Now we move to a really important concept related to a matrix, and it is called the condition number. Condition number. So before explaining this, we need a particular theorem whose proof we will do. So let A be an invertible n cross n matrix. A be an invertible n cross n matrix, and let x and x tilde, okay, let me write it in the next line. Let x and x tilde be the solutions of the system systems ax equal to b and ax tilde equal to b tilde, respectively, which means x is a solution of the first system and y is the x tilde is a solution for the second system, obviously. Where b and b tilde are given vectors. Are given vectors. So this is our hypothesis. So then x minus x tilde by norm x, it is less than equal to norm A times norm A inverse, norm of A inverse times b minus b tilde for any fixed vector norm and the matrix norm subordinate to this vector norm. Okay. Okay, let us do a quick proof of this, and then we'll see what does this theorem precisely mean. So since A is invertible, we have x minus x tilde, so x will be A inverse B and x tilde will be A inverse B tilde, which is same as A inverse of B minus B tilde, because matrix multiplication is associative. Yeah. Now if you take the norm on both sides, taking norm on both sides, we get norm of x minus x tilde is same as norm of A inverse B minus B tilde, and we use this inequality, so it is same as norm of A inverse times norm of B minus B tilde, and this holds for every, yeah, so this we have. So if you consider this, norm x, see, because ax was b, so norm x is actually what I want to say, that b is actually norm b is actually norm ax, which is less than equal to norm a times norm x. So this implies 1 upon norm x is less than norm a times norm b. So you can, okay, so maybe just a minute. Yeah, now it's fine. So maybe let us call it 1 and let us call it 2. So using 1 and 2, we get that see, by 1, this is the numerator is less than equal to this norm of A inverse upon B minus B tilde, and 1 by norm x by 2 is less than equal to norm A by norm B, and which is precisely what we had to prove. Okay, so this is precisely what we had to prove. So just a minute. Hello. Yes sir.